In the previous video, we talked about phase changes. So when we go from a liquid to a gas, we have to deal with the gas molecules that we have, created from that liquid. So this next topic is vapor pressure. And what we can talk about here is that in a liquid, the intermolecular forces between molecules enable it to remain in the liquid phase. If a certain kinetic energy barrier is reached, there will be enough energy to convert the liquid into a gas. And we typically look at these and analyze these by drawing up a plot. And the plot that we're going to look at on the x-axis has kinetic energy. And on the y-axis, we're going to look at the fraction of the molecules. And more importantly, we're going to look at the fraction of the molecules in each particular phase. So if we're at a lower temperature, we can see a graph that kind of looks something like this. Okay? And if we define this point right here to be our minimum kinetic energy barrier for the molecules to go from a liquid to a gas. So if this is a low temperature substance here, we have liquid molecules here on the left side of this dotted line. So over here we have our liquid molecules, and down here on this right side we have our gaseous molecules. Now when we heat this, our curve is going to shift a little bit. So let's kind of take a look here. If we heat this, here's our more higher temperature curve that's going to look something like this. So over here on the right hand side of this dotted line is our minimum kinetic energy barrier for the molecules that go from a liquid to a gas. So over here on this end of the curve, we can see that there's a much greater percentage of these molecules that are in the gaseous state. So at the low temperature, we only have a small fraction of molecules in the gaseous state, but at a large temperature, or a higher temperature, we additionally have these extra molecules in the gaseous state. So it kind of takes this whole section of the curve right here. So what we can say about this is that as we increase the temperature, we're going to increase the kinetic energy, and more molecules can escape to the gaseous phase. And this will go on continuously as a gas molecule, can be, or as a molecule can be converted from a liquid to a gas, right? And we can go from a solid to a liquid and look at the same curve here. But what happens here is that when we produce these gas molecules, we can have them escape, and we're going to see some type of vapor pressure. So we need to kind of analyze this, and in a particular system, we can convert liquid molecules to gaseous molecules and vaporize them, or we can condense them back from a gas to a liquid. And this process is happening kind of at the same time, right? So we have to analyze this all together, and what we can say is that when the rate of vaporization equals the rate of condensation, dynamic equilibrium is established. And we can use this equilibrium condition to tie back into the vapor pressure. So the vapor pressure of a liquid is the pressure exerted by its vapor when the liquid and vapor are in dynamic equilibrium. So when the rate of vaporization equals the rate of condensation, we call this the vapor pressure. And as we increase the intermolecular forces, or as the intermolecular forces are stronger, the vapor pressure is going to be lower. Because in the liquid phase, everything's attracted to each other very, very strong. We're not going to have a high vapor pressure. Okay? But as we increase the temperature, our vapor pressure is going to increase. So from this, we can determine something called a boiling point. And the boiling point is going to be dictated by, some external pressure, right? So a liquid's going to boil when its vapor pressure equals the external pressure acting on the surface of the liquid, okay? And we're going to observe, bubbling or bubbles of vapor forming within the liquid, all right? And this temperature at which a liquid boils is going to increase with increasing external pressure. So we have to come up with a term called a normal boiling point. Because the boiling point is going to be influenced by our external pressure. So our normal boiling point is the boiling point of a liquid at 1 atmosphere of pressure, or 760 torr. So we have to come up with this baseline, and whenever you see boiling points, you're typically going to see a normal boiling point expressed, and that's when the vapor pressure is going to be at 1 atmosphere or 760 torr. We can do boiling points at any pressures, but just to compare different substances, it's nice to have a baseline or a standard, and that standard is what we're going to call a normal boiling point. Okay, you've seen pressure cookers and things like this where we can change the properties of the liquid based on the temperature, but when we refer to a boiling point, you'll typically see the normal boiling point, which gives us a basis of comparison for one substance to another.